At the edge of a still, sunlit wetland, where reeds rise in dense clusters and the air hangs heavy with moisture, a predator patrols a space that has changed far less than the world beyond it. The surface of the water reflects a sky broken only by the slow drift of clouds, but just above that mirror, motion is constant, precise, and sudden. A scarlet dragonfly cuts through the air with a velocity that seems almost detached from the softness of its surroundings, its body held rigid as its wings beat in a blur that the human eye struggles to resolve. It does not wander. It hunts. The dragonfly represents one of the most intact predatory designs still active on Earth, a body plan that has endured since long before mammals dominated land or birds filled the skies. Its presence feels less like an adaptation to the modern world and more like a continuation of an older one, when vast swamp forests covered continents and oxygen levels supported even larger, more formidable aerial hunters. In those ancient ecosystems, speed and reaction time defined survival, and the dragonfly's physiology still carries the imprint of that selective pressure with remarkable clarity. Its head is dominated by compound eyes that occupy nearly the entire surface, each one composed of thousands of individual facets. These facets do not simply form a mosaic image. They create a highly sensitive detection system capable of registering motion with extreme precision. The dragonfly does not track prey in the way a mammal might, with focused attention and depth perception centered forward. Instead, it perceives movement across almost the entire sphere around it, constructing a dynamic map of trajectories and velocities. This allows it to predict where prey will be, not where it is, adjusting its flight path in advance with a level of interception accuracy that rivals far more complex vertebrate hunters. Its flight is equally revealing. Unlike most insects, which rely on indirect flight muscles that deform the thorax to drive wing beats, dragonflies use direct flight muscles attached at the base of each wing. This grants them an unusual degree of control, allowing the forewings and hindwings to operate independently. The result is a flight system capable of hovering, gliding, accelerating, and even flying backward, all while maintaining stability in turbulent air. Each adjustment is subtle but precise, with wing angles shifting to manipulate lift and thrust in real time. In the dense, humid air above wetlands, where thermal currents are weak and obstacles are constant, this flexibility is not a luxury, but a necessity. As it patrols, the dragonfly's movements reveal a strategy refined over immense spans of time. It does not chase randomly. Instead, it establishes a territory, often returning to the same perches and flight paths, creating a predictable patrol circuit. From these vantage points, it launches rapid sorties, intercepting smaller insects such as midges, mosquitoes, and flies. The capture itself happens mid-air, its spiny legs forming a basket that snaps shut around the prey. There is no wasted motion. The prey is consumed while still in flight, the dragonfly continuing its patrol without landing, maintaining a continuous cycle of detection, interception, and consumption. This efficiency is not merely a product of speed, but of energy management. Wetland environments, though rich in life, can fluctuate in resource availability. By minimizing unnecessary movement and maximizing successful captures, the dragonfly maintains a high metabolic output without excessive energy loss. Even its coloration, the vivid scarlet of its body, plays a role in thermoregulation and signaling, absorbing sunlight to regulate internal temperature, while also communicating territorial ownership to rivals. Beneath the surface, another chapter of this ancient design unfolds. Dragonflies begin life as aquatic nymphs, predatory forms that bear little resemblance to their aerial counterparts. In this submerged phase, they possess extendable lower jaws capable of shooting forward to seize prey, capturing tadpoles, small fish, and other aquatic organisms. This dual existence, first as a water-bound ambush predator and later as an aerial interceptor, reflects a life cycle deeply tied to the wetland structure, exploiting two distinct ecological niches within the same environment. It is a strategy that reduces competition and increases survival across developmental stages. Seen in motion, the scarlet dragonfly does not appear primitive. It appears refined, almost excessive in its precision, as though designed for conditions more demanding than those it currently inhabits. And in many ways it was. The modern wetland is a fragment of a once dominant world, a remnant of ancient ecosystems where such capabilities were essential rather than exceptional. The dragonfly has not adapted away from that past. It has carried it forward, unchanged in its fundamental mechanics, continuing to operate with the same ruthless efficiency. In the stillness of the wetland, where the boundaries between water, air, and vegetation blur, the dragonfly remains a constant. It is not simply surviving in the modern world. It is executing a design that was perfected long before it, moving through the air with a confidence that suggests it belongs to a deeper timeline, one where the rules of survival were written in speed, precision, and the ability to intercept a moving target in a world that never stood still. In the dim, layered interior of a tropical forest, where sunlight filters downward in fragmented beams and the air remains thick with humidity, a different kind of predator constructs its presence not through movement, but through architecture. Between two branches, suspended across an open corridor where insects routinely pass, a golden silk orb-weaver has drawn a structure that does not simply occupy space, but transforms it. The web is nearly invisible until the angle of light reveals it, a radial geometry stretched across an aerial pathway that countless small creatures unknowingly rely upon. Here, the forest itself becomes part of the hunting mechanism, and the spider waits at its center, motionless, as if it were an extension of the design rather than its creator. The orb-weaver's body appears elongated and delicate, its long legs extended outward in a posture that maximizes contact with the silk. Each leg rests lightly on specific strands, not randomly, but in positions that allow the spider to detect minute variations in tension. The web is not a passive trap. It is a sensory system, an externalized extension of the spider's nervous network. Vibrations travel through the silk with remarkable fidelity, carrying information about the size, location, and struggle patterns of anything that touches it. A small insect produces rapid, erratic signals, while a larger one generates slower, more forceful distortions. Through this, the spider does not need to see its prey in detail. It reads the web as a living map of disturbances. The silk itself represents one of the most refined biological materials in the natural world. Produced as a liquid protein within specialized glands, it is extruded and rapidly solidifies into threads that combine strength and elasticity in a balance rarely matched by synthetic materials. Some strands are designed to absorb impact, stretching under the force of a flying insect without breaking, while others remain rigid, maintaining the overall structure of the web. The spiral threads, coated in a subtle adhesive, ensure that once contact is made, escape becomes increasingly unlikely. In the humid air of the forest, this adhesive remains effective, resisting desiccation and maintaining its grip even as environmental conditions fluctuate. Unlike active hunters, the orb-weaver does not expend energy in pursuit. Its strategy relies on the predictable movement of other organisms through the forest's layered spaces. Flying insects, navigating between branches and leaves, often follow habitual routes shaped by light, wind, and the distribution of resources, such as nectar or decaying organic matter. The spider positions its web precisely within these pathways, effectively intercepting traffic that would otherwise pass unnoticed. This is not chance placement. Over time, the spider adjusts its construction, responding to changes in airflow, vegetation growth, and prey availability, refining the web's position to maximize success. When an insect collides with the web, the response is immediate but measured. The spider does not rush blindly. It interprets the vibrations first, distinguishing between viable prey and potential threats, such as larger animals that could damage the web. Only when the signals confirm an appropriate target does it move, advancing along non-sticky support threads with controlled precision. Upon reaching the trapped insect, it delivers a rapid bite, injecting venom that begins to immobilize and pre-digest the prey's internal tissues. The spider then wraps the body in silk, securing it and preventing further struggle, effectively storing it for consumption. This approach reflects an evolutionary pathway that prioritizes efficiency over speed. Energy is invested not in repeated chases, but in the construction and maintenance of a system that operates continuously. Even the act of rebuilding the web, which may occur daily or after significant damage, is part of this strategy. Old silk is often consumed and recycled, allowing the spider to reclaim valuable proteins and reduce the metabolic cost of producing new material. In this way, the web is both tool and resource, an extension of the spider's physiology that can be dismantled and reformed as needed. The golden coloration of the silk, visible under certain lighting conditions, may also play a role beyond structural function. It can reflect specific wavelengths of light, potentially making the web less visible to some insects, while more attractive to others that are drawn to subtle visual cues resembling gaps in vegetation or pathways toward light. This interplay between visibility and concealment adds another layer of complexity, suggesting that the web is not merely hidden, but actively integrated into the perceptual world of its prey. Within this system, the orb-weaver becomes less of a hunter in the traditional sense and more of an engineer embedded within the forest's architecture. Its survival depends on understanding and manipulating the physical properties of its environment, turning empty space into a functional extension of its body. The forest provides the framework, but the spider defines the geometry, creating zones of capture that operate continuously, even in its stillness. In the broader context of evolution, this represents a different form of persistence. While some ancient designs rely on speed, strength, or direct confrontation, the orb-weaver endures by mastering the invisible forces that govern movement and interaction in a complex environment. Tension, vibration, and spatial arrangement become the primary tools, allowing the spider to remain effective without the need for constant motion. It is a quiet dominance, one that reshapes the ecosystem in subtle ways, capturing and redistributing energy as insects are removed from circulation and incorporated into the spider's life cycle. Suspended in its web, the golden silk orb-weaver appears almost secondary to the structure it inhabits, yet it is the central intelligence behind it. The web holds the forest in a temporary balance of forces, each strand carrying information, each intersection calibrated for purpose. In this space, the act of hunting has been transformed into an act of design, where success depends not on the pursuit of prey, but on the ability to predict and intercept the paths it will inevitably take. In the deep interior of an old forest, where fallen trunks lie layered in slow decay and the scent of damp wood lingers in the air, a different kind of life unfolds beneath the surface. Here, time moves not in days or seasons, but in years of gradual breakdown, as fungi thread through timber and insects carve hidden pathways within. From within one such log, softened by moisture and colonized by unseen networks of decay, a stag beetle has completed a transformation that began long before the present canopy took its current shape. It emerges not as a creature of speed or subtlety, but as a relic of continuity, carrying a body designed for a world where forests were allowed to age, collapse, and renew without interruption. The adult stag beetle appears almost excessive in its construction. Its body is thick, armored, and darkly polished, reflecting faint highlights in the filtered light of the forest floor. Most striking are the mandibles, enlarged into branching structures that resemble antlers more than functional mouthparts. At first glance, they seem impractical, even ornamental, but their purpose becomes clear in the brief and intense phase of adult life that follows emergence. These are not tools for feeding or defense against predators. They are instruments of competition, shaped by generations of conflict over access to mates. The life of the stag beetle begins far removed from this moment. As larvae, they inhabit the interior of decaying wood, feeding slowly on softened fibers that have been partially broken down by fungi and microbial activity. This diet is low in immediate energy, requiring long periods of development to accumulate the resources needed for metamorphosis. In some species, this stage can last several years, during which the larva grows steadily, insulated from the external environment by the surrounding timber. The wood itself acts as both shelter and sustenance, buffering temperature fluctuations and providing a stable, if limited, food source. This prolonged developmental phase ties the species directly to the presence of mature forests. Deadwood is not incidental here, it is essential. Without large, undisturbed trees that can fall and decay over extended periods, The conditions necessary for larval growth simply do not exist. In managed landscapes where fallen timber is removed or decomposition cycles are disrupted, the stag beetle's life cycle is interrupted before it can even begin. Its dependence on long-term ecological processes makes it an indicator of forest continuity, a species whose presence reflects not just current conditions, but the history of the habitat itself. When the adult finally emerges, it does so into a world that operates on a different timescale. The adult phase is brief, often lasting only a few weeks, and is focused almost entirely on reproduction. During this period, feeding is minimal or absent, with energy reserves accumulated during the larval stage sustaining all activity. The large mandibles of the males come into play here as individuals compete for access to females, often at sap flows or other localized resources where potential mates gather. Encounters between males are direct and forceful. Two individuals approach, raising their front bodies and engaging with their mandibles in a contest that is less about inflicting damage and more about leverage and control. The goal is to lift and dislodge the opponent, forcing it off the substrate and away from the contested site. The structure of the mandibles, with their curved and branching forms, is adapted for this purpose, allowing one beetle to grasp and manipulate another with surprising precision. These contests can appear slow, almost deliberate, but they are the culmination of years of development, each movement reflecting the outcome of selective pressures that favor size, strength, and mechanical advantage. Despite their formidable appearance, stag beetles are not dominant predators within their environment. They are vulnerable to birds, mammals, and other insects, and their heavy bodies and limited flight capabilities make them less agile than many potential threats. Their strategy is not based on avoiding all risk, but on maximizing reproductive success within a narrow window of opportunity. The energy invested in oversized mandibles and armored bodies is directed toward ensuring that, during this brief period, an individual can outcompete rivals and pass on its genetic traits. The forest around them continues its slow cycle, largely indifferent to these momentary struggles. Fungi spread through fallen logs, breaking down complex organic compounds into simpler forms that can be reabsorbed into the ecosystem. Other insects, from smaller beetles to larvae of various species, share the same decaying wood, each occupying a slightly different niche. In this layered system, the stag beetle represents one expression of a broader process, its life intertwined with the gradual transformation of solid timber into soil. Seen in this context, the stag beetle is less a curiosity and more a continuation of an older ecological pattern. Its reliance on deadwood, its extended larval development, and its brief competitive adult phase all reflect conditions that were once widespread when forests were allowed to mature and decay without constant human intervention. The neat, managed landscapes of modern parks, with their cleared understories and removed debris, offer little space for such a life cycle to unfold. The stag beetle persists where fragments of that older world remain, in forests where fallen trunks are left to lie, and time is allowed to work at its own pace. As dusk settles and the air cools, the beetle moves with a deliberate heaviness across the uneven surface of bark and moss. Its form, shaped by forces that predate most modern ecosystems, carries with it a history of competition, endurance, and dependence on processes that extend far beyond a single lifespan. In the quiet of the forest floor, among the slow collapse of wood into earth, the stag beetle continues a pattern that has endured not through adaptation to change, but through its connection to a world that has, in many places, almost disappeared. In the fading light of late afternoon, when the heat of the day begins to soften and shadows stretch across open meadows, a small, fast-moving shape hovers with a precision that seems almost mechanical. Among clusters of flowering plants, where nectar is held deep within narrow tubes, a hummingbird Hawk-moth maintains its position in mid-air, its wings beating so rapidly they dissolve into a translucent blur. From a distance, it can be mistaken for a bird, its hovering posture and darting movements echoing a completely different lineage. Yet this resemblance is not imitation in the sense of deception. It is convergence, a shared solution to the same problem, arrived at through entirely separate evolutionary paths. The moth's body is compact and muscular, built around the demands of sustained hovering flight. Unlike many insects that rely on brief bursts of motion followed by rest, the hummingbird hawk-moth operates within a narrow energetic margin, where continuous wing activity is required to remain suspended in front of a flower. Its wings move in a figure-8 pattern, generating lift on both the downstroke and the upstroke, a trait that allows it to hover with remarkable stability. Each adjustment in position is minute and controlled, compensating for shifts in air currents and the subtle movement of the plant itself. In this space, precision is not optional. A slight misalignment would break contact with the flower and disrupt feeding. Extending from its head is a long, flexible proboscis, coiled when not in use, but rapidly unfurled when the moth approaches a bloom. This structure allows access to nectar hidden deep within floral tubes, resources that are inaccessible to many other insects. As the proboscis probes into the flower, the moth's head and thorax come into contact with pollen-bearing structures, facilitating pollination. This interaction is not incidental. It reflects a long-standing relationship between certain plants and their pollinators, where the shape and depth of flowers have co-evolved with the feeding apparatus of the animals that visit them. Many of the flowers frequented by hummingbird hawk moths are adapted to low-light conditions, opening or becoming most active during twilight. Their colors may appear muted to human eyes, but they often emit strong scents that guide pollinators through chemical cues. The moth, in turn, possesses sensory adaptations that allow it to detect these signals, navigating towards suitable feeding sites even as visual contrast diminishes. Its compound eyes are tuned to detect movement and low levels of light, while its antennae contribute to balance and orientation, stabilizing flight in an environment where visual references can be unreliable. The energy demands of this lifestyle are considerable. Hovering flight requires a constant expenditure of energy, supported by a high metabolic rate that necessitates frequent feeding. The moth must move efficiently between flowers, maximizing nectar intake while minimizing time and energy lost in transit. Its flight path often follows a predictable circuit, visiting multiple plants in sequence before returning to previously exploited sites as nectar replenishes. This pattern reflects not only the moth's behavior, but also the dynamics of the plants themselves, which produce nectar at rates that balance attraction of pollinators with conservation of resources. Temperature plays a critical role in this system. As a cold-blooded organism, the hummingbird hawk-moth depends on external conditions to maintain the muscle activity required for flight. Before becoming fully active, it may engage in a form of behavioral thermoregulation, vibrating its flight muscles to generate heat and raise its internal temperature. This allows it to operate in cooler periods of the day, extending its feeding window into times when competition from other insects may be reduced. The ability to function under these conditions provides access to resources that are not constantly contested, reinforcing its niche within the ecosystem. Predation remains an ever-present risk. Birds, spiders, and other insectivores are capable of capturing moths in flight or at rest. The hummingbird hawk-moth's speed and agility offer some protection, allowing it to evade many threats through rapid, unpredictable movements. Its resemblance to a bird may also play a subtle role, potentially deterring certain predators that are less inclined to attack a target that appears larger or unfamiliar. However, these advantages are not absolute, and many individuals fall prey before completing their life cycle. Despite these challenges, the hummingbird hawk-moth represents a design that has endured with relatively little fundamental change. Its combination of hovering flight, elongated feeding structures, and sensory adaptations aligns closely with the requirements of pollination systems that have existed for millions of years. In this sense, it is not a relic of a forgotten world in appearance, but in function. The relationship it embodies between insect and flower remains one of the most stable and widespread interactions in terrestrial ecosystems. As the light continues to fade and the meadow shifts toward evening, the moth remains active, moving from one bloom to the next with consistent rhythm. Each visit transfers pollen, contributing to the reproductive success of the plants, while each intake of nectar sustains the moth's own existence. This exchange, repeated countless times across landscapes and generations, forms a continuous thread connecting past and present. It is a system that has proven effective enough to persist, requiring no radical reinvention, only the maintenance of a finely balanced set of traits. In the quiet space between daylight and darkness, the hummingbird Hawk-moth hovers, suspended in a moment that reflects an ancient agreement between species. Its presence is not an anomaly, but a continuation, a demonstration that some designs achieve a level of efficiency and integration that allows them to endure, unchanged in their essence, across vast spans of time. In a sunlit meadow where grasses sway in slow, coordinated waves and the air vibrates with the movement of countless small insects, a structure hangs between stems that appears at first like a flaw in the landscape. A zigzag of bright silk cuts through the otherwise delicate geometry of the web, catching the light in a way that seems almost deliberate, almost conspicuous. At the center of this structure, aligned with that bold line, a wasp spider rests motionless, its body marked with sharp bands of yellow, black, and white. It does not hide in the traditional sense. Instead, it occupies a narrow threshold between visibility and confusion, where being seen can be as effective as being concealed. The meadow itself is an environment defined by openness and movement. Unlike the layered complexity of forests, where shadows and surfaces provide endless opportunities for concealment, grasslands expose organisms to a more uniform and often harsher visual field. Wind continuously shifts the background, bending stems and altering the position of light, while flying insects move through predictable corridors shaped by vegetation height and density. Within this space, the wasp spider constructs a web that does more than intercept prey. It actively interacts with the visual and physical dynamics of its surroundings. The web's central feature, the stabilimentum, is a dense, zigzag band of silk that reflects ultraviolet light, a wavelength visible to many insects, but not to the human eye. This structure has long been a subject of observation and debate, but within the context of the meadow, its function becomes more apparent. Flying insects navigating through grasslands often rely on visual cues to identify open pathways and avoid obstacles. The stabilimentum may mimic such cues, appearing as a gap or a safe route through the vegetation. Drawn toward this apparent opening, an insect instead encounters the surrounding capture threads, which are nearly invisible against the shifting background. The spider's own body reinforces this effect. Its bold striping resembles that of stinging insects, particularly wasps, creating a visual signal that may deter certain predators, while simultaneously blending with the stabilimentum's reflective properties. When positioned along the central axis of the web, the spider's form becomes integrated into the overall pattern, breaking up its outline and making it more difficult to distinguish as a separate entity. This is not camouflage in the sense of disappearing into the background, but rather a form of visual manipulation, where the predator becomes part of a signal that misleads both prey and potential threats. Despite its apparent stillness, the wasp spider is constantly engaged with its environment through the web. Vibrations travel along the silk, conveying detailed information about any disturbance. The spider's legs, extended outward, maintain contact with key points of the structure, allowing it to detect even minor changes in tension. When an insect strikes the web, the resulting vibrations differ depending on the size, wing beat frequency, and struggle pattern of the prey. The spider interprets these signals, distinguishing between viable targets and non-prey disturbances, such as falling debris or larger animals brushing against the web. Upon confirming a suitable capture, the spider moves with sudden precision. It approaches a long non-adhesive line of silk, avoiding entanglement, and begins to wrap the prey in layers of fine thread. This process immobilizes the insect quickly, reducing the risk of escape or injury to the spider. A venomous bite follows, initiating the breakdown of internal tissues, which will later be consumed. The entire sequence unfolds with efficiency, reflecting a strategy that minimizes direct confrontation while maximizing control over the outcome. The placement of the web is as critical as its structure. The wasp spider selects locations where insect traffic is concentrated, often between taller grass stems or near flowering plants that attract pollinators. These sites represent intersections of movement, where the probability of contact is highest. Over time, the spider may adjust the position or orientation of its web in response to changes in vegetation growth, wind patterns, and prey availability, fine-tuning its trap to the shifting conditions of the meadow. Temperature and light also influence the spider's behavior. As a cold-blooded organism, it relies on external warmth to maintain the muscle activity necessary for rapid response. Positioning the web in areas that receive adequate sunlight ensures that the spider can remain active during peak periods of insect movement. At the same time, the reflective properties of the stabilimentum may vary with the angle of light, altering its visibility and effectiveness throughout the day. Predators, including birds and larger insects, pose a constant threat. The wasp-like appearance of the spider may provide some level of deterrence, as many predators avoid stinging insects due to the risk of injury. However, this mimicry is not foolproof, and the spider's survival depends on a combination of factors, including its positioning, stillness, and the protective complexity of its web. In some cases, individuals may rapidly drop from the web when disturbed, hanging by a single thread to avoid detection, only to climb back once the threat has passed. Within the broader ecosystem, the wasp spider plays a role in regulating insect populations, particularly those that move through the meadow in search of food or mates. By capturing a range of flying insects, it contributes to the balance of species within this environment, influencing the distribution and behavior of its prey. Its presence reflects the health and structure of the grassland, as it depends on the continuity of open spaces and the availability of suitable anchoring points for its web. Seen in the context of evolutionary history, the wasp spider's strategy represents a form of persistence rooted in the physical properties of its environment. Rather than relying on speed or strength, it exploits light, tension, and the predictable movement of other organisms. The stabilimentum, the web's geometry, and the spider's own coloration all work together to create a system that operates at the intersection of visibility and deception. This approach suggests a lineage shaped by open habitats that have existed for vast periods, where the ability to manipulate perception and intercept movement within a dynamic landscape has proven more effective than direct pursuit. As the meadow continues its constant motion, the web remains anchored between swaying stems, its lines catching the light in fleeting flashes. The spider at its center does not chase or wander. It waits within a structure that extends its reach far beyond the limits of its body, turning empty space into an active field of capture. In this quiet, suspended geometry, the wasp spider continues a method of hunting that feels inseparable from the ancient physics of open land, where survival depends not on being unseen but on controlling what others believe they see. In the heavy stillness of a tropical night, where the air holds warmth long after sunset and the scent of fermenting sap drifts through the understory, a form emerges that seems built less for speed than for force. On the rough bark of a tree exuding sweet, sticky fluid, a rhinoceros beetle climbs with deliberate effort, its body thick and weighty, its movements slow but controlled. Around it, other insects gather, drawn to the same resource, but none carry the same sense of mass or presence. The beetle's silhouette, crowned with a curved horn that extends from its head, resembles a structure more than a creature, as if shaped for impact rather than agility. The forest in which it moves is defined by abundance and competition. Sap flows, created by wounds in tree bark or natural fissures, become focal points of activity, attracting beetles, moths, flies, and other organisms that feed on the rich sugars. These sites are temporary but highly contested, and the density of life around them creates a constant pressure to secure access. In such an environment, subtlety offers little advantage. Instead, the rhinoceros beetle relies on strength, leverage, and a body capable of withstanding repeated physical encounters. Its exoskeleton is thick and rigid, composed of hardened chitin that provides both protection and structural support. This armor is not merely defensive. It forms the framework that allows the beetle to exert force without damaging itself. Beneath this outer layer, powerful muscles attach to internal surfaces, enabling movements that, while not fast, are forceful and sustained. The horn, which varies in shape and size among species, is a direct extension of this system. It is not used for feeding or defense against predators, but for interaction with other beetles, particularly during competition for access to sap flows or mates. When two males encounter each other at a feeding site, the interaction is immediate and physical. They position themselves face to face, lowering their heads and bringing their horns into contact. The contest that follows is a test of strength and leverage, each individual attempting to lift, push, or overturn the other. The horn acts as a lever, allowing one beetle to gain purchase beneath the body of its opponent, exploiting slight imbalances to disrupt its footing. The bark beneath them provides limited traction, and a well-placed movement can dislodge a rival, sending it tumbling away from the contested resource. These encounters are not random acts of aggression, but structured competitions shaped by evolutionary pressures. Larger horns and stronger bodies increase the likelihood of success, granting access to feeding sites and, by extension, to females that may be present in the same area. However, the development of such features comes at a cost. Energy invested in growing a large horn cannot be used elsewhere, and individuals must accumulate sufficient resources during their larval stage to support this investment. As with many insects, the adult phase is relatively brief, and the outcomes of these contests directly influence reproductive success. Before reaching this stage, the rhinoceros beetle spends the majority of its life hidden within decaying organic matter. As larvae, they inhabit soil rich in decomposing wood and plant material, feeding on a mixture of organic detritus and microbial life. This environment provides both nourishment and protection, allowing the larva to grow over an extended period. The decomposition process itself is driven by a complex community of fungi, bacteria, and other organisms, breaking down tough plant fibers into forms that can be consumed. In this way, the beetle's early life is closely tied to the recycling of nutrients within the forest ecosystem. This connection to decay and regeneration reflects a broader ecological role. By feeding on decomposing material, rhinoceros beetle larvae contribute to the breakdown of organic matter, aiding in the return of nutrients to the soil. As adults, their feeding on sap does not significantly harm the trees, but rather exploits existing openings, participating in a network of interactions that includes plants, microorganisms, and other insects. Their presence at sap flows can also influence the behavior of other species, as the outcome of their contests determines which individuals gain access to the resource. The beetle's apparent heaviness, which might seem like a disadvantage in a world that often rewards speed, is instead a reflection of the conditions in which it evolved. In dense, humid forests, where vegetation is abundant and competition is localized around specific resources, the ability to exert force in confined spaces becomes more valuable than rapid movement over long distances. The rhinoceros beetle does not need to chase prey or evade predators through speed. Its strategy is to dominate key sites, securing access through strength and resilience. Thermoregulation also plays a role in its activity patterns. Being dependent on external temperatures, the beetle is most active during warm periods, particularly at night when humidity remains high and the risk of desiccation is reduced. The forest canopy traps heat, creating a stable microclimate that allows for sustained activity even after the sun has set. In this environment, the beetle's dark, robust body retains warmth, supporting muscle function during extended periods of movement and interaction. Predators, including birds and mammals, are capable of overcoming even such heavily armored prey, and the beetle's size does not guarantee safety. However, its durability and the difficulty of handling such a rigid, horned body can deter some attackers or prolong the encounter long enough for escape. More often, survival depends on remaining within the relative security of the forest floor and tree trunks, where concealment and structural complexity reduce exposure. Seen against the backdrop of modern landscapes, the rhinoceros beetle appears almost out of place, its design suggesting conditions that are not easily replicated in managed environments. It is a product of forests, where biomass accumulates and decays in continuous cycles, where resources are concentrated and competition is direct. Its form, heavy and deliberate, reflects a world where strength was a primary currency, and where the ability to move another body, even slightly, could determine success. As it anchors itself at the edge of a sap flow, the beetle becomes part of a larger system, one defined by the slow release of energy from plant to insect from structure to motion. The horn, the armor, and the steady, forceful movements all point to a lineage that has persisted not by adapting to speed or efficiency in the modern sense, but by maintaining a design suited to environments of density and abundance. In the dim light of the forest, surrounded by the quiet activity of countless other organisms, the rhinoceros beetle continues to operate as it always has. A living mechanism shaped by a world that, in many places, has already begun to fade. In the stillness of a dense, shaded woodland, where light filters down in thin, fragmented strands, and the air carries the quiet weight of layered vegetation, movement becomes difficult to detect. Leaves overlap in irregular patterns, branches intersect at unpredictable angles, and shadows settle into shapes that rarely resolve into anything distinct. Within this visual complexity, a form exists that does not merely hide among the plants, but appears to belong to them entirely. A stick insect rests along a narrow branch, its elongated body aligned so precisely with the wood that it dissolves into the surrounding structure, becoming less an organism and more a continuation of the plant itself. Its body is segmented and slender, each section resembling the natural irregularities of a twig. Subtle variations in color, from muted greens to dry browns, reflect the tones of living and dead plant alike, allowing the insect to match not a single surface, but a range of conditions within its habitat. Even its legs extend outward at angles that mimic small offshoots, reinforcing the illusion of a broken or branching stem. This is not a simple disguise, but a full commitment to a single strategy: to exist without being recognized as something separate from the vegetation. The forest environment in which the stick insect lives is defined by visual noise. Countless lines, edges, and overlapping shapes create a backdrop where identifying individual objects requires attention and movement. Predators that rely on sight must distinguish prey from this complexity, detecting patterns that stand out against the background. The stick insect exploits this challenge by removing itself from the category of recognizable forms. It does not attempt to outpace predators or deter them through defense. Instead, it avoids triggering the initial detection that would lead to pursuit. This strategy extends beyond appearance into behavior. The stick insect remains motionless for extended periods, aligning its body with the orientation of surrounding branches. When it does move, the motion is slow and deliberate, often accompanied by a gentle swaying that mirrors the effect of wind on vegetation. This movement is not random. It reinforces the illusion of being part of the plant, integrating the insect's actions into the broader dynamics of the environment. Even in the presence of potential threats, the stick insect may rely on stillness rather than escape, trusting that its resemblance to inanimate objects will prevent recognition. Feeding occurs primarily at night, when visual predators are less active and the risk of detection is reduced. The insect consumes leaves, often from the same plants it imitates, creating a direct link between its form and its food source. This diet is relatively low in nutritional value, requiring the insect to process large amounts of plant material to meet its energy needs. As a result, its metabolism is adapted to a slower pace of life, where energy conservation is essential. Growth and development proceed gradually, with multiple molts allowing the insect to increase in size while maintaining its characteristic shape. Reproduction introduces another layer of complexity to this quiet existence. In some species of stick insects, females are capable of parthenogenesis, producing offspring without fertilization. This ability allows populations to persist even when mates are scarce, a useful adaptation in environments where individuals may be widely dispersed and encounters infrequent. The eggs themselves often resemble seeds, complete with structures that attract ants. These ants carry the eggs into their nests, providing protection from predators and environmental extremes. Once the eggs hatch, the young insects emerge and make their way back to the vegetation, beginning the cycle anew. Predation, despite the effectiveness of camouflage, remains a constant pressure. Birds, reptiles, and other insectivores occasionally detect stick insects, particularly when movement or environmental disturbance breaks the illusion. In response, some species have developed secondary defenses, such as the ability to drop from branches and remain motionless on the forest floor, or to shed a limb that continues to twitch, distracting the predator while the insect escapes. These mechanisms are rarely the first line of defense, but they provide additional layers of protection when concealment fails. The relationship between the stick insect and its environment is one of deep integration. It does not simply occupy the forest, it becomes part of its visual and structural fabric. This level of mimicry suggests an evolutionary history shaped by environments where vegetation was dense, continuous, and relatively stable over long periods. In such conditions, the ability to blend seamlessly into plant life offered a reliable path to survival, reducing the need for speed, power, or complex behavioral strategies. Modern landscapes, with their fragmented habitats and altered vegetation patterns, often disrupt these conditions. The continuity of plant structures is broken, and the visual complexity that supports such mimicry is reduced. Yet in pockets of undisturbed woodland, where branches still overlap in layered arrangements and shadows maintain their depth, the stick insect continues to exist as it always has, relying on a strategy that predates many of the changes imposed by human activity. There is an almost paradoxical quality to this form of survival. By becoming less distinct, the stick insect achieves persistence. It does not compete directly, nor does it dominate through force. Instead, it withdraws into the background, allowing other organisms to overlook it entirely. This absence of recognition becomes its greatest strength, enabling it to move through its life cycle with minimal interference. As the forest settles into night and the last traces of daylight fade, the stick insect begins to move more freely, its slow steps tracing paths along branches that have supported countless generations before it. Each motion is measured, each pause deliberate, maintaining the balance between activity and invisibility. In this quiet, layered world, where the boundaries between organism and environment blur, the stick insect remains a living example of a strategy rooted in ancient vegetation, a form so completely adapted to its surroundings that it no longer appears separate from them. Beneath the surface of a sun-warmed landscape, where roots thread through soil and stones hold the memory of past seasons, a quiet process unfolds far beyond immediate perception. In this hidden layer, surrounded by darkness and the slow movement of moisture through earth, cicada nymphs live for years without ever seeing the sky. They move through narrow tunnels, guided by chemical cues from plant roots, their bodies adapted for a life that depends on patience rather than motion. Here, time stretches, measured not in days, but in cycles of growth so gradual that change is almost imperceptible. Each nymph anchors itself to a root, inserting its specialized mouthparts deep into the plant tissue to access the flow of xylem fluid. This liquid, drawn upward from the soil, contains dissolved nutrients but is dilute and low in energy. To sustain itself, the cicada must process large volumes of this fluid, extracting what little nourishment it can while expelling excess water. This feeding strategy ties the insect directly to the physiology of the plant, making it both a consumer and a participant in the subterranean exchange of resources. Around it, the soil hosts a complex community of organisms, from microorganisms breaking down organic matter to other insects following similar hidden paths, all contributing to a system that remains largely unseen. The nymph's body reflects the demands of this environment. Its legs are thick and adapted for digging, allowing it to navigate through compacted soil and create chambers where it can rest and feed. Its exoskeleton is durable, protecting it from abrasion and the pressures of the surrounding the earth. Sensory structures, though limited compared to those of the adult, allow it to detect subtle changes in moisture, temperature, and root proximity, guiding its movements within a world defined by touch and chemical gradients rather than sight. Above ground, the landscape shifts through seasons, temperatures rise and fall, and entire communities of organisms appear and disappear. Yet the cicada remains below, insulated from many of these changes, its development proceeding according to internal processes that are synchronized with long-term environmental patterns. In some species, this underground phase can last for over a decade, a duration that far exceeds the lifespan of many predators that might otherwise threaten them. This extended development is not simply a delay, but a strategy that spreads risk across time, ensuring that when emergence finally occurs, it happens in overwhelming numbers. The transition from this hidden existence to the open air is sudden and synchronized. Triggered by specific soil temperatures and seasonal cues, nymphs begin to emerge en masse, climbing toward the surface in a coordinated movement that transforms the landscape almost overnight. As they reach the air, they seek vertical structures, such as tree trunks, grasses, or any available support, anchoring themselves as they prepare for their final transformation. The exoskeleton splits along the back, and the adult cicada slowly pulls itself free, expanding soft wings that will soon harden and take on their functional form. This emergence represents a critical shift in both form and function. The adult cicada is built for a brief but intense period of activity, focused primarily on reproduction. Its body is swollen compared to the nymph, its wings broad and capable of sustained flight, and its sensory systems adapted for life above ground. The mouthparts, while still capable of feeding, are less central to its survival than during the nymph stage. Instead, energy accumulated over years of subterranean feeding supports the adult through its short lifespan. One of the most striking features of the adult cicada is its ability to produce sound. Males generate calls using specialized structures called tymbals, membranes that are rapidly deformed and released by muscular action. This produces a series of clicks that combine into continuous tones, amplified by the hollow structure of the abdomen. In dense populations, these calls merge into a collective sound that can dominate the acoustic landscape, reaching levels that alter the behavior of other animals. Birds may adjust their hunting patterns, and predators that rely on sound can become overwhelmed by the sheer intensity of the noise. This acoustic display serves a clear purpose, attracting females for mating, but it also plays a role in the broader survival strategy of the species. By emerging in large numbers and producing overwhelming signals, cicadas reduce the effectiveness of predators. Even if many individuals are consumed, the sheer volume ensures that enough survive to reproduce. This phenomenon, known as predator satiation, is a direct consequence of their synchronized life cycles, a strategy that relies on coordination across entire populations. The presence of cicadas above ground is brief but impactful. As they feed, mate, and eventually die, their bodies return nutrients to the soil, contributing to the same system that supported them during their development. Their emergence also affects plant dynamics, as the sudden influx of feeding insects and the subsequent return of organic matter influence nutrient availability and growth patterns. In this way, the cicada's life cycle connects multiple layers of the ecosystem, from deep underground to the canopy above. What makes the cicada particularly remarkable is not its appearance, but its relationship with time. Its life is structured around intervals that extend beyond the immediate experience of most organisms, aligning with environmental cycles that operate on longer scales. This temporal strategy reflects a lineage that has persisted by synchronizing with patterns that remain relatively stable over long periods, even as surface conditions change. As the final days of the adult phase pass and the sound gradually fades, the landscape returns to a quieter state. Eggs laid within plant tissue will eventually hatch, and the next generation of nymphs will descend into the soil, beginning the cycle anew. Beneath the surface, the process continues, largely hidden but profoundly connected to the rhythms of the environment. In this interplay between concealment and sudden appearance, between years of stillness and brief moments of intense activity, the cicada operates as a biological clock, marking time in a way that reflects ancient patterns of survival. Its presence above ground is only a fraction of its existence, a visible reminder of processes that have been unfolding unseen, governed by cycles that extend far beyond the span of a single season. In a thicket where stems rise vertically in tight clusters and leaves overlap in layered planes, movement is measured not in distance, but in precision. The air is dense with the subtle motion of small insects navigating between surfaces, each trajectory shaped by the geometry of vegetation. Within this vertical maze, a form remains fixed, aligned with the structure of the plants so completely that it appears less like an organism and more like a deliberate interruption in the pattern. A praying mantis grips a stem with careful balance, its elongated body held upright, its forelegs folded in front of it in a posture that suggests stillness but conceals readiness. The mantis does not rely on speed across open ground or endurance over long distances. Its design is centered on proximity, on the ability to detect and respond to movement within a narrow, controlled space. Its head, triangular and highly mobile, can rotate to track activity without requiring the rest of the body to shift. This separation of observation and movement reduces the likelihood of detection, allowing the mantis to remain visually integrated with its surroundings while continuously monitoring the space around it. Its large compound eyes are positioned forward, providing overlapping fields of view that enable a form of depth perception unusual among insects. This binocular vision allows the mantis to judge distance with remarkable accuracy, a critical ability for an ambush predator that must strike with precision rather than adjustment. The forelegs, often described as raptorial, are the primary instruments of this strategy. Each is equipped with spines that form a grasping structure capable of closing rapidly around prey. When not in use, they remain folded, reducing their profile and maintaining the illusion of inactivity. The muscles that control these limbs are adapted for sudden release, storing energy that can be deployed in a fraction of a second. When a target enters the appropriate range, the mantis extends its forelegs in a rapid motion, capturing the prey before it can react. The strike is not a chase, but a calculated interception, dependent on timing and distance rather than sustained pursuit. This method of hunting reflects an environment where opportunities are brief and unpredictable. In dense vegetation, insects move through narrow corridors, appearing and disappearing behind leaves and stems. The mantis positions itself at points where these paths intersect, often near flowers or areas of high insect activity. From this vantage, it can exploit the movement patterns of other organisms, intercepting them as they pass through the confined space. The success of this strategy depends on patience, as the mantis may remain in the same position for extended periods, waiting for the right moment to act. Its body contributes to this approach not through bulk or armor, but through alignment with the environment. The elongated figure, with its narrow thorax and abdomen, mirrors the vertical lines of stems, while coloration varies to match the surrounding vegetation. Some individuals exhibit shades of green that blend with fresh leaves, while others take on brown tones that resemble with aging plant material. This variation allows the mantis to integrate into different stages of vegetation, maintaining its concealment across changing conditions. Feeding behavior reveals a level of adaptability that extends beyond simple predation. The mantis consumes a wide range of prey, from small flies to larger insects, and in some cases even vertebrates such as small reptiles or amphibians. This opportunistic diet reflects a capacity to handle different types of prey, adjusting its grip and feeding strategy as needed. The mandibles are strong and capable of breaking down various tissues, allowing the mantis to extract maximum nutritional value from each capture. This flexibility ensures that it can exploit whatever resources are available within its immediate environment. Reproductive behavior introduces a different dynamic, one that is often associated with the species, but is less universal than commonly assumed. In some cases, females may consume males during or after mating, a behavior that provides additional nutrients that can be invested in egg production. However, this is not a constant outcome and depends on factors such as food availability and individual condition. The eggs are laid within a protective structure known as an ootheca, a foam-like casing that hardens to shield the developing embryos from environmental extremes and predation. This structure is often attached to vegetation, integrating the next generation into the same vertical framework that defines the adult's life. Temperature and light influence the mantis's activity patterns. As a cold-blooded organism, it relies on external heat to maintain the speed of its physiological processes. Positioning within sunlit areas allows it to absorb warmth, increasing its responsiveness and the power of its strikes. At the same time, excessive exposure can lead to overheating, requiring the mantis to adjust its position within the vegetation to maintain a balance. This interaction with the microclimate of the habitat further ties its behavior to the structure of the environment. Predators, including birds and larger insects, pose a threat despite the mantis's capabilities. Its reliance on stillness and camouflage offers protection, but when detected, it may attempt to evade through sudden movement or, in some species, display defensive behaviors that make it appear larger or more intimidating. These responses are secondary to its primary strategy of remaining unnoticed, reinforcing the importance of its integration with the surrounding vegetation. The mantis represents a form of predation that is stripped to its essential elements: detection, positioning, and rapid execution. Its design does not incorporate unnecessary features, focusing instead on the precise coordination of sensory input and mechanical action. This simplicity is not a limitation, but a reflection of an evolutionary pathway that has refined a specific approach to hunting over long periods. Within the dense vertical spaces of its habitat, the mantis operates as both observer and participant, its presence defined by the absence of movement until the exact moment it becomes necessary. It does not dominate the environment through force or speed, but through an understanding of how movement occurs within it, placing itself where that movement can be intercepted. In this way, it embodies a form of predation that feels anchored in older ecosystems, where the complexity of vegetation and the density of insect life created conditions in which patience and precision were the most effective tools. As the surrounding plants shift with the wind and light continues to change, the mantis remains poised, its form aligned with the structures that support it. It is a hunter that has reduced its existence to a series of calculated moments, each one dependent on the interaction between body and environment. In this quiet, layered space, it continues a method of survival that has endured not through adaptation to new conditions, but through the persistence of a design that remains effective wherever the geometry of vegetation and the movement of prey intersect. In the dim interior of a tropical forest, where fallen leaves accumulate in thick layers and the ground remains damp beneath a canopy that filters most of the sunlight, movement is slow and deliberate. The air is dense with the scent of decomposition, a constant process that breaks down the remains of plants and returns them to the soil. Within this environment, where visibility is limited and space is defined by crevices, bark, and decaying wood, a form emerges that seems less concerned with speed than with persistence. A Madagascar cockroach moves across the forest floor, its body broad and low, its surface smooth and polished as though shaped by constant contact with the structures around it. The cockroach's design is immediately distinct from the more specialized predators and pollinators that occupy other parts of the ecosystem. Its body is flattened and shielded, allowing it to press into narrow spaces beneath bark or between layers of leaf litter. The exoskeleton, composed of hardened plates, provides both protection and flexibility, enabling it to navigate uneven terrain while resisting pressure from above. This structure is not optimized for rapid movement or aerial activity, but for durability in a confined and often crowded environment where physical contact is unavoidable. The forest floor is a place of constant transformation. Leaves fall, fungi spread, and microorganisms break down complex organic materials into simpler compounds that can be reabsorbed by plants. The cockroach operates within this cycle as a detritivore, feeding on decaying plant matter and contributing to the redistribution of nutrients. Its digestive system is adapted to process materials that are difficult to break down, relying on symbiotic microorganisms within its gut to assist in the decomposition of cellulose and other complex compounds. This relationship allows the cockroach to extract energy from resources that many other organisms cannot utilize directly. Unlike insects that depend on specific prey or floral resources, the cockroach's diet is broad and opportunistic. It consumes a variety of organic materials, from fallen leaves to decomposing wood, and even the remains of other animals. This flexibility reduces its dependence on any single resource, allowing it to persist in environments where conditions may change or where competition for more specialized food sources is intense. In this sense, the cockroach does not compete directly with many other species, but occupies a niche that supports the overall functioning of the ecosystem. Its behavior reflects the constraints and opportunities of its habitat. The cockroach is primarily active during periods of low light, when the risk of predation is reduced and humidity remains high. During the day, it seeks shelter in protected spaces, minimizing exposure to predators such as birds, reptiles, and small mammals. At night, it emerges to forage, moving with a steady, purposeful gait that prioritizes stability over speed. Its antennae extend forward, constantly probing the environment, detecting chemical cues and physical obstacles that guide its movement through the complicated structure of the forest floor. One of the most distinctive features of the Madagascar cockroach is its ability to produce sound. When threatened or during interactions with other individuals, it can force air through specialized openings in its body, creating a hissing noise. This sound serves multiple functions, including deterring predators and facilitating communication within the species. The mechanism itself is simple, relying on the rapid expulsion of air, but its effect can be significant, startling potential threats, and signaling the presence of a robust, responsive organism. Reproduction in the Madagascar cockroach involves a level of care that contrasts with the often solitary nature of its life. Females retain their eggs within their bodies until they are ready to hatch, providing a degree of protection during development. The young, once born, resemble smaller versions of the adults and undergo a series of molts as they grow. This direct development, without a distinct larval stage, allows the species to maintain continuity within the same habitat, with each generation occupying similar ecological roles. The cockroach's physiology also reflects its adaptation to a humid, sheltered environment. Its body retains moisture effectively, reducing the risk of desiccation in an ecosystem where water availability can vary across microhabitats. The ability to regulate water loss is critical for survival, particularly during periods when conditions become less favorable. By remaining within protected spaces and limiting exposure, the cockroach maintains the internal balance necessary for its metabolic processes. Predation remains a constant pressure, but the cockroach's design mitigates some of these risks. Its flattened body makes it difficult to grasp, while its tough exoskeleton provides a barrier against many forms of attack. When combined with its ability to retreat quickly into narrow crevices, these features create a defense strategy based on avoidance and resistance rather than confrontation. The hissing sound adds an additional layer, introducing an element of unpredictability that can disrupt the approach of a predator. Within the broader context of the forest ecosystem, the Madagascar cockroach represents a form of stability. While other species may fluctuate in number or distribution, responding to changes in resources or environmental conditions, the cockroach persists through its generalist approach and its integration into the process of decomposition. It does not rely on specific interactions that may be disrupted, but on the continuous breakdown of organic matter, a process that remains constant as long as the forest exists. There is a quiet resilience in this design. The cockroach does not display the speed of aerial hunters or the intricate structures of web-building spiders. It does not rely on elaborate sensory systems or specialized hunting strategies. Instead, it embodies a different kind of success, one based on endurance, flexibility, and the ability to function within the most fundamental processes of the ecosystem. Its presence is a reminder that survival does not always depend on refinement toward a narrow purpose, but can also arise from a broad capacity to persist under a wide range of conditions. As it moves through the dark, humid layers of the forest floor, the Madagascar cockroach carries with it a lineage that has endured through vast changes in the world above. Its form, shaped by environments where decomposition and shelter define the limits of life, remains largely unchanged because it continues to meet the demands of its niche. In this final layer of the ecosystem, where matter returns to its simplest forms and new growth begins, the cockroach persists as a quiet constant, a living expression of survival, not through dominance or specialization, but through the ability to remain.